In this video, which is going to be a little bit longer than my other usual ones, we're going to be looking at Le Chatelier's principle. It's a very simple kind of principle, but there's a lot of tricks and nuances for the 4 different things we're going to look at here. I'll show this at the very end. We're going to go through all of these except the catalyst on the very bottom. And we'll see how this works. All right, so this is a good little thing to maybe print out or write down as you're going through this lecture here, okay? So first of all, let's take a look at the actual principle itself. It says that a reaction will respond to counteract the change. So for example, in physics, we say every force has an equal and opposite force. In economics, we have supply and demand that counteract each other, okay? When the supply goes up, demand goes down, and vice versa. So they seem to be counteracting each other. In biology, for example, we have homeostasis. When the bunny rabbit population increases, there's suddenly all this food. So then the tiger population increases, and then that's going to cause the bunny population to go down as they eat all their bunnies, right? And in chemistry, we have the equilibrium principle. Basically, you're going to do the opposite thing. For example, if I tell my kids, hey, can you be quiet? Can you keep your voices down? In response to that, they're going to start being more noisy, okay? And I tell them, hey, can you really be quiet here? And then in response, they just seem to be even louder, okay? So chemical reactions are stubborn. If you try to increase the concentration, they're like, I'm going to do something to decrease that concentration. If you increase the pressure, they're going to do something in response to decrease that pressure. If you decrease the temperature, for example, they're going to go, I'm going to do something to increase the temperature. So they always do something to respond opposite to the impetus or what you're doing to it to cause it to change, okay? It's weird, but you'll see how this works. All right, let's first talk about concentration changes. So let's consider a reaction at equilibrium. We have 3 different gases, we have an equilibrium constant, and we even have a temperature here, okay? Now, what happens if we add chlorine, okay? If we add chlorine, that's a reactant, it's here on the left. What's going to happen is that you're going to shift right away from the increase, okay? What happens is that chlorine goes down a little bit, okay? So if you give somebody a lot of money, they're like, I'm going to go buy, take my friends out, I'm going to go see a movie or something, and the money in their wallet is going to go down a little bit, right? So they do something opposite to what you're doing. If we add chlorine here, this reaction is going to shift to the right to bring that chlorine concentration down a bit, all right? Here's the summary of that chart, just a little bit. So if you increase the concentration of a substance, you shift away from that substance. All right, what happens if we add PCl5? Well, PCl5 is a product. So again, we shift left away from the increase, right? When you shift away from the increase, the PCl5 concentration or pressure is going to drop a little bit, okay? And I've snipped, again, this little phrase here. So if you increase the concentration of a substance, you shift away from that substance. So in this case, the reaction shifts left, all right? What happens if we remove something? Well, if we remove PCl3, that's a reactant. That's on the left side of the equation. And so the reaction is going to shift left towards the decrease. In response, the PCl3 goes up a little bit, right? So, if you take money out of your son's wallet or something like that, they'll be like, man, I have no money to buy some candy or something. So maybe they'll want to go out and mow lawns or get a job or work some more, and maybe they'll get money in response to that, right? So if you decrease the concentration of a substance, the chemical reaction will shift towards the substance. In this case, it's shifting to the left, all right? Now, I just want to point out something students oftentimes get confused about. Watch out for solids and liquids. Remember that solids and liquids are part of the balanced chemical equation, but they don't enter into equilibrium expressions because they don't have a concentration, they don't have a pressure, right? A solid is not homogeneously spread throughout the whole reaction mixture of the container, right? It might just be on the bottom or something. So if we have this chemical reaction here, very carefully note that the PCl3 here is a solid. And so what happens if we add solid PCl3 to this? Well, there's going to be no shift, all right? So remember again, solids are not in the equilibrium expressions. So are liquids, okay? So let's take a look at some questions for you. This is the chemical equilibrium, and I'm asking you, what happens if we remove PCl5? What happens if we add PCl3? I look forward to hearing your responses on this. All right, what about temperature? We can increase or decrease the temperature of a chemical reaction by heating it up or cooling it down in an ice bath, for example. And that's what we'll do in Lab 5. So let's review here about exothermic reactions. If the delta H is negative, we say that that's exothermic and heat is released. Heat is going to be a product, or on the right-hand side of the chemical equation. And if delta H is positive, we say that's endothermic. We say heat is absorbed, and heat is going to be written on the left side of the thermochemical equation, okay? Now, let's look at this chemical reaction here. We are given some information about the heat of reaction. So delta H is plus 52.8 kilojoules. So what you want to do here is pretend like heat is a physical substance that you could hold in your hand, put in a jar, and weigh on a balance, you know? It's not, but let's pretend like heat is a physical substance. If the reaction is endothermic, we're going to put heat on the reactant side of the chemical reaction or equilibrium, okay? And now we have heat, all right? And so what we want to do here is just think about adding heat or removing heat. So for example, what would happen if we heated our reaction mixture? Well, heating kind of means adding heat, and so heat's on the left side of the equation. So this reaction would shift to the right because, again, we shift away from the increase. Here's from that summary table. If you increase the temperature of a system, you shift away from the heat. Okay? Let's do the same thing, but let's see what happens if we cooled our reaction. Well, if we cool our reaction, we're removing heat, right? We're placing that test tube in an ice bath, and the ice-water mixture is going to be, removing heat from our test tube. If we remove heat, this reaction is going to shift to the left because, you shift towards the decrease. So here's from the summary chart. If you decrease the temperature, you're going to shift towards the heat. On the right little box there, it says why that is, okay? All right, consider a reaction at equilibrium. So we've got nitrogen oxide in equilibrium with nitrogen gas and oxygen gas. And delta H is negative 210.7 kilojoules. Negative. Okay, so what do? We pretend, again, that heat is a physical substance. Heat for an exothermic reaction is written on the right. So we do that, and then we can ask some questions here, okay? What would happen if we heated our reaction? So again, remember, heating means adding heat. So heat is on the right side of this chemical equation. And so what we would do is think about shifting away from the increase. So that means the reaction will shift left, okay? And on the bottom, I've taken a little snapshot of that summary chart. I'll show you at the very end of this presentation. If you increase the temperature of a system, you shift away from the heat or away from the energy. What would happen if we cooled our reaction? Well, the opposite thing would happen. If you cool a reaction, you're basically removing heat, and we pretend like the heat's only on the right side of the chemical equation. Okay, so if we remove heat, it means you're going to shift towards the decrease. It's going to shift right. So here's from the summary table. If you decrease the temperature of a system, you shift towards the heat or the energy as it's drawn or written in your thermochemical equation, okay? So it's a little weird and it looks kind of inconsistent, but trust me, there is no inconsistency. We always shift away from the heat. So when both of these reactions are heated, they're both heated, okay? The top reaction shifts to the left, the bottom reaction shifts to the right. You might be at this point thinking, well, wait a minute, shouldn't they all shift the same way? Well, no, because for an exothermic reaction, heat's on one side of the equation, and for an endothermic reaction, heat's on the other side of the equation. So they have opposite influences on the direction of the shifting when you heat these chemical reactions, okay? So make sure you're very clear when you see the negative sign or the positive sign there, which side of the equation you put heat on, and then just use the same principle again of Le Chatelier's principle. You do the opposite. You shift away from the increase or you shift towards the decrease. All right, here are some questions for you. Now that you understand this a little bit, which way will this reaction shift if cooled? So we've got hydrogen and iodine vapors in equilibrium with HI. And then we have another question, which way will this reaction shift if it's heated? C2H4 and chlorine and, you know, all that stuff, okay? I look forward to reading your responses on this. All right, now let's talk about pressure changes. Before we jump into pressure changes, let's review what we know about gases. If you decrease the volume, you're increasing the pressure because you're squishing the gases into a smaller volume and they're closer together and bouncing into the walls more often, okay? And if you increase the volume, you decrease the pressure because the individual gas molecules are going to be bouncing against the walls much less, okay? Now we can change the pressure in a piston type reactor. So that's how we're going to change the pressure. We're not going to be adding things or removing things. We're just going to think about maybe squishing the reaction mixture or expanding the reaction mixture, okay? We're going to assume that the number of moles and the temperature remains constant during this change. So let's look at a chemical reaction. We've got carbon monoxide and water vapor reacting to form carbon dioxide and hydrogen gas. And so we want to ask what happens if we increase the volume. We know that's going to change the pressure in some way. We'll try to think about that later, but what happens? Well, what you want to do is count the number of moles of gas on each side of the chemical equation. There's one CO and one H2O, so there's a total of 2 gas molecules on the left. And we do the same thing on the right. There's 1 carbon dioxide and 1 hydrogen molecule, so the total moles of gas is 2 on the right. And since n equals 2 on both sides, nothing is going to happen. There's equal pressure on each side, and there's no direction this chemical equation can shift to change that fact, all right? What about this chemical reaction? What happens if we increase the volume? All right, so once again, count up the number of moles of gas on each side of your chemical equation. There's 2 moles of gas on the left, 1 from the CO, 1 for the Cl2. And on the right, we have n equals 1 because there's just 1 molecule of gas on the right. So there's a different number on the left and a different number on the right. So here we're going to see a shift. Go ahead now and label the high pressure side. Remember, if you have more moles of a gas in a container, it's higher pressure. So higher number, higher pressure. Just remember that. So higher pressure is on the left, lower pressure is on the right. Now we need to think about this volume thing in the question. Increasing the volume is the same thing as decreasing the pressure, okay? Decreasing the pressure is lowering the pressure. If I tell a reaction, hey, I'm going to lower the pressure on you, it's going to respond oppositely, and it's going to shift to the high pressure side, okay? So it shifts toward more moles of a gas or the high pressure side because you're trying to lower the pressure, so it's going to do something opposite. So from the summary table, if you decrease the pressure of a system, the reaction is going to shift towards more moles of a gas, okay? The reason is basically it's just doing the opposite of what you're trying to do. All right. Let's look at another example here. What happens if we decrease the volume of this chemical equation here? We've got carbon, H2O, CO, and H2. The first thing you want to do is count the number of moles of gas on each side of the equation. Wait a minute. Why did I cross that out? In bold, on the bottom of this slide in purple, I've been saying count the moles of gas on each side of the chemical equation. Remember that solids don't have pressure, okay? They're just a powder that's in that reaction mixture. And so if you increase the pressure or decrease the pressure, the fact that you have solid in there does not alter that fact, okay? So count only the moles of a gas in your chemical equilibrium. On the left, I count 1 mole of water or 1 molecule of water. So N is 1 on the left. On the right, I have N equals 2. Okay, I have 1 CO and 1 H2. So that's a total of 2. I want to go ahead and label the low pressure side and the high pressure side. And then I want to carefully think about this decreasing the volume business, okay? If you decrease the volume, you're increasing the pressure. Think a bicycle pump, all right? You're pushing down on it and you're decreasing the volume and the pressure is increasing, okay? So that means high pressure. So if you're telling a reaction, hey, I want to make you high pressure, what does the reaction do? It does the opposite, okay? It's going to shift towards the lower side or the left. I forgot to put my little green arrow in here, but I wrote it. Okay, so you're going to shift towards the less moles of gas or the low pressure side. And here's a snippet from that summary table basically saying the same thing. All right. So here are my questions for you now that you understand a little bit about the pressure and volume influences on the direction of shifting of gaseous chemical equilibria. We have hydrogen peroxide in equilibrium with water vapor and oxygen gas. And I would like you to tell me what happens if we increase the volume, what happens if we increase the pressure, okay? So I look forward to reading these responses on your notes as you take notes from this lecture. Our fourth criteria or thing we want to look at is addition of inert gas. So consider the following equation. We've got nitrogen, chlorine, and nitrogen trichloride. They're all gases in here. And so what happens if we add argon gas? If we add argon gas, we know that a gas inside of a container is going to increase the total pressure. But guess what? The total pressure the total pressure does change, as I mentioned, because you're putting more moles of argon or argon gas into a closed container, but the concentration of each reactant does not change. The concentration of nitrogen, the concentration of chlorine, and the concentration of NCl3 does not change when you just by the fact of putting argon in there, okay? And the partial pressure of each reactant does not change. Argon is not part of this chemical equation. It's not a reactant, it's not a product, so that's why we say it's inert. It's not going to influence this reaction at all, and so we say there's no shift. No shift will occur. So there you have it. You've got all of these different stresses. You can increase the concentration of a substance. You can decrease the concentration of a substance. You can increase the pressure. You can decrease the pressure. You can increase the temperature, or you can decrease the temperature. And the reaction is always going to be stubborn and oppose that change and shift in an opposite fashion. If you increase the concentration, it shifts away from the increase. If you decrease the concentration, it's going to shift towards the decrease. If you increase the pressure, it's going to shift towards the low pressure side. And if you decrease the pressure, it's going to shift to the high pressure side. If you increase the temperature, shift away from the heat. If you decrease the temperature, shift towards the heat. I didn't talk about a catalyst, but a catalyst is like an inert substance. It's not part of the balanced overall chemical equation, so there's no shift. So that in a nutshell is Le Chatelier's principle. I hope this helps you understand more the Open Stax chemistry textbook or whatever textbook you may be reading. Thanks for watching. Please consider thumbs upping this video and possibly even subscribing. Have a great day, everybody.